but the process is the same for your data. So just notice what numbers I'm combining and you'll do the same thing. And you do along with me if you'd like. Okay, so what we have found so far, what we measured in the lab is how many beans were per isotope, and then the total mass of that particular isotope. Now, one of the other flaws with this lab, like we said, our isotopes don't look the same. For us, they did. The other thing that is a little bit off is the fact that if this really was an atom, our final answer that we calculate would be the same for everyone in the room. Because the same atom always has the same atomic mass. But being that they're just beans and I just grabbed some and threw them in a bag, our final answers are not going to be the same. Okay? So just kind of recognize the difference between true atoms versus our simulation here. Okay? So the first thing we want to do is we want to know on average how much does one blacium weigh. So to find the average of just one, what we are going to do here is we're going to take the total mass of all the blacium, so for me, 42.5, and divide it by how many blaciums you had. So for me, 210. So if you want to do that for you and plug it in and get some answers here. So take the total mass of it and divide it by how many. And you can just keep 2 decimal places for all of it if you'd like. So that tells us on average, if I weigh a black bean, for me, in my bag, it should weigh about 0.2 grams. A lima beans should weigh about 1.26 grams per bean. Okay? Now, I want to show you something that is the wrong way to do it, because I think a lot of times understanding not how to do it can better help you understand how to do it. So in general, can someone explain to us, by raise a hand, how do I calculate an average of something? Like what's the process you do, Kens? Good, so we would add them all up. So we have 4 isotopes, right? Blacium, brownium, whitium, limium. So a normal average would be to add up your 4 isotopes and divide it by 4. Okay, so a normal average would be 0.2 plus 0.3 plus 0.36, 0.126 divided by 4. I would like you to actually calculate your normal average and then just write it in like the little side of your box. Okay, so everyone do that for your group real quick and figure out what is your normal average.
So like of all of the different beans?
So if we take just those 4 masses, add them up and divide by how many? So normal averages, you add up and divide by how many you have. Now, the reason why we don't use a normal average when we're talking about the mass of isotopes is because it doesn't give you the best picture. What that number should represent is that if I reach into my bag of beans, I pull out a bean and I put it on the scale, on average, it should weigh 0.53 grams, according to that number. So why is that a bad number to represent our beanium?
Because it assumes you have an equal number of each isotope.
Good. Jeff, what were you going to add to that?
I was just saying because limium is like way far away from that number.
Yeah, like limium's way far away. But also, though, what's the probability of me actually pulling out a limium?
1 in 4% of 86 or so.
Pretty low, right? I only have 5 limiums. So this normal average, the problem of it, it's cutting it into 4 equal parts. But isotopes are not equal in their weight or in their amounts. For me, I have way more blacium than I have of the other ones. So my average should be shifted towards whatever blacium actually weighs. And 0.53 is a lot higher than 0.2. Because for me, if I close my eyes and reach into my bag, I'm most likely going to pull out a blacium. So when you calculate a weighted average, we don't divide it by 4 or by how many you have. Instead, you are going to multiply it by what's known as its percent abundance. So to find the percent abundance, we look at, you need to know how many total beans you have in your bag. So if you don't have that yet, you just add those up. Okay, I think mine's like 286. Is that right?
Yeah.
So for me, I would take 210 and divide by the total. So you can do that now for your okay. Now, those are the percent abundances. To represent it as a real percentage, what do you have to do with a decimal?
Move it over right now.
Right, times it by 100, move it 2. So this is 73%, 17%, 7%, and 1%.
The totals don't equal.
Did I type something in wrong maybe?
You're 2%.
Oh, it's just because of rounding. If I kept more decimals, then it would be more accurate. But good observation there, McKay. Okay, I'm going to leave them, though, in a decimal form because when you use percentages in a mathematical equation, they need to be in a percentage, in a decimal form. But keep in mind what it represents, right? This represents that 73% of my beanium is the isotope blacium. Now, this is what I want you to write down in your notes as well as this equation. There's actually 2 slides that we did not cover in your notes where it says average atomic mass, which would be a great place to write down this equation. Okay? So the way you calculate an average atomic mass is you are going to take the percent abundance of the isotope, so percent, and multiply it by the mass of that individual isotope. Okay, you can even write like isotopes mass. Then plus the percent times isotope mass for the next isotope. So this would be like isotope 1. This would be my second isotope. And you have to continue until you've done all the isotopes it has. So percent times mass, percent times mass, percent times mass. Add them together, and that would be your weighted average.
And we're multiplying it by the total mass or the individual?
The individual mass. Because in terms of an isotope, what is the isotope's mass number is in a sense what we'd be using. So for my beanium sample, this is what I would be plugging into this equation. I would take the percent, so 0.73, times by 0.20. So So if you didn't hear McKay's question, he was asking, is it the individual or the total? It's always the individual because that's what we're trying to isolate, is how much does one beanium weigh on average. So I do this times that, this times that, this times that, this times that, and then add them all together. In that box on your lab paper where you're calculating the average atomic mass, so where it says atomic mass of beanium, I would like you to write out your work in that so we can make sure that I can see that you have the right equation. So this is what I would write in that box. I would write 0.73 times 0.2, 0.33 times 0.17, 0.36 times 0.07 plus 1.01 plug that all in and let's compare it to what our true average was. Great question, Belle. We don't. So because the percentages, in a sense, are doing the dividing for us. So good question. Yeah, Taylor.
Do you do the average mass or the total mass?
The average of just one. Yep, because we're looking for just the mass of one bean.
You have to divide it all by one, don't you?
Depends on how you do it. If you leave them in decimal form, you don't have to. But you are totally right, Carter. If you put them in as a true percentage, then you definitely have to divide by 100.
Like that.
Okay, so for me, I got 0.24. Now, in terms of this lab, our unit will be grams, because that's what we measured our beans in. But if you want to make a note on your notes, for an atom, the unit here is known as an AMU. It stands for atomic mass unit. But for our beans, we measure them in grams, so that's why it's in grams. Questions on that equation, everybody? Now, why is this a better picture for my beanium than the true average up here?
Because you have 210 black beans
Yeah.
and 5 mine.
Because I have tons of black beans. So most of the time when I find blackium in the world, or beanium in the world, most of the time it's going to be this particular isotope. And so the average should be shifted towards it. This process, everyone, is the exact same way how your grade is calculated. Because your grade is a weighted grade. It's not a true grade where everything is equal, it's weighted. And so that's why test scores shift your grades so much more than warm-ups do. Because warm-ups are only 10%, so it has that same relationship. Okay? Questions on average atomic mass? Okay, here are your steps of what you're going to do now. Step 1 is you're going to finish the summary questions on the Beanium lab. We're turning that in today. After you complete the Beanium lab, bring it up to the front. You'll turn it into our number strip. Then you can start working on things that are due next time in preparation for our Unit 3 quiz. So there's one more paper in your packet called Atomic Structure. I will post the answers to this, and let me show you where we can find those for those that had a hard time.